Hello Intertubers and welcome to the nerdy interlude. So this is about Lanchester's square law. So Lanchester had made a lot of simulations of combat under various assumptions. The one we cared about is the square law, which arises in a situation where you've got two armies and every soldier is always able to attack someone in the other army. So this is usually range combat, because if it's like a bunch of guys with swords hacking away at each other, if one arm is much bigger than the other, then it might actually be impossible for some of the people in the large army to get near the people in the small army. So yeah, large numbers also helpful, because we'll be using calculus on integers, which is kind of silly, but on large numbers it'll work out. So yeah, range combat with aimed shots is the typical thing that's modelling here. Like, in the specific case of Deuteros, armies of drones shooting lasers at each other. That sounds like the classic example to me, assuming that lasers have whatever range they need to, and there's certainly no terrain advantage or anything like that in space. So yeah, we got two teams, we call them A and B, and those will be those numbers will be the size of the armies. So the rate at which Team A dies depends on one thing, and it depends only on how quickly Team B is killing them, which depends on which we think is proportional to size and quality. So yeah, dA by dt is minus KBB, where KB is some constant. I guess it's actually the per capita kill rate. So it has units of 1 over time, if you care about that. And similarly, the same equation but reversed for how quickly the people on Team B are getting killed. Now, in the specific case of Deuteros, about 99% of the time we're fighting with same power drones against same power drones, which means we're just going to call both of those constants K. So, how to solve this? Reasonably simple. Anyone who's done A-level maths, I think, should be able to do this. I think A-level maths was where I learned this.
Here comes the science bit. Concentrate.
So yeah, differentiate one, substitute the other, and solve. And to be more specific, that's one equation. Differentiate it, get minus k dB by dt, and then we just substitute in the other, minus k squared a. And then the other equation exactly the same, second derivative of b is proportional to b, and there's going to be two solutions to that, basically e to the minus kt and e to the plus kt. Of course, any linear combination of solutions is good, so invent the coefficients p and q for a, but once we've chosen it for a, we've also chosen b. It must be the derivative of a, divided by a factor of k anyway. Oh, sorry, minus the derivative of b. So yeah, if you differentiate a, you get minus k p k kt. Then another minus k q e to the kt, which conveniently is minus that, well, minus k times that. And we can equate coefficients like that times 0. We'll say a0 and b0 are going to be the starting values. So just add or subtract those equations, and we can figure out what p and q are very quickly. So we'll deal with the asymmetrical case first. I briefly mentioned the symmetrical case. It's very boring. Basically, there's no e to the kt, only q e to the minus kt for both sides. That's it. So in that case, the armies just kill each other, or very slowly dwindle down to 0. So yes, they've got that equation, and we're aiming for a hyperbolic function, and this is always possible. If you've got non-zero amounts of e to the kt and e to the minus kt, then at some point they're going to be equal to each other. So to find that, we split the p and the q up into the geometric mean. I can't highlight this, but the geometric mean and two ugly things that are reciprocals of each other. Then next, take those square root of p over q's and put them into the exponent. So you notice on the first one, square root of p over q somehow becomes square root of q over p. That's because we're subtracting it. The second time round, q over p remains q over p, even though we're subtracting it, and that's because it's multiplied by e to the minus kt. So we've got two minus signs on it there. And that's pretty ugly. Let's make it even uglier by pulling out a factor of 2 and also dividing by 2. But there is method to this madness. We got this horribly ugly thing, but with some substitutions, we call the leading coefficient r and call that absolutely disgusting thing that we're being subtracted from t, capital T. And what is that? Well, that's just a hyperbolic cosine or cosh function. And probably won't be a huge surprise that b is the corresponding sine h function. You can get that pretty easily once you've... I mean, you could do exactly the same logic here, or you could just differentiate cosh. Because when you differentiate cosh, you get sine h and vice versa. So those are the solutions. Although those constants have to be defined. Now r is the one we cared about. R is a square root of a0 squared minus b0 squared. And t is ugly, but we don't really care. So t is how long the battle is going to take. And we really don't care about that because it's like only a few seconds in Deuteros anyway. And of course the simulation actually slows down when there's too many drones on the screen, so time really is almost irrelevant. But r is very, very important because r is going to be the final value of a when b gets reduced to 0. So yeah, to actually talk about the square law, we've got these two equations now. I guess if there's one trig identity you should know, it's cos squared plus sine squared equals 1. And if there's one hyperbolic trig identity you should know, it's cosh squared minus sine h squared equals 1. Which means we can do something with a squared minus b squared. It's equal to something made out of cosh squared minus sine h squared, which is going to be just r squared, which is the original values. So that's actually a constant. And the conclusion, strength of an army is in some sense proportional to the square of its size. For example, if you want to know how many casualties the army is going to take, if you work with the squares, it's pretty simple. It starts with a0 squared, fights a smaller army of size b0 or square size b0 squared. So just subtract one square from the other. But you do have to remember to square root at the end of everything to get the old value back. Yeah, final value of a is that. Might be worth some demonstrations here. So let's head over to Desmos, which is the quickest way I can get a graphing calculator. So suppose we have 200 drones and the enemy has 100. So we've got 200 squared minus 100 squared. T minus x minus log square root of and exactly the same, but minus sine h. Alright, I may need to zoom out to actually see 200 and 100. Right, and we're going to tweak the timescale just a bit. Like a factor of 100 should do it. And as this is not 200, and this is not 100. Desmos LN. Right, want to use the proper log function, and not one based on the absolutely ridiculous choice of 10. We see that at time 0 we start out with 200 and get 100 as we should. Yeah, I'll just spread this out. So we find that this dwindles all the way down to 0, but this only goes down to 173. So if you fight 100 drones with 200, you're only taking 27 casualties. That's not a very big number, and that's because of the square law. 173 is actually 200 times root 3. In fact, even if you were to do something like 190, what do we have here? The middle point is 62, which means an advantage of 10 drones actually results in an advantage of 62 at the end. Like, we'd expect to only lose 140 and keep 62, which is a substantial number. So yeah, numbers really do matter. By the way, you should ignore everything that happens after this point. See, what actually happens in the differential equation is that the population of Team B goes below 0, because Team A is still killing them, and because this population is going below 0, when the negative army fights, it actually magically raises people in the real army from the dead, so the numbers go up again. Yeah, that's absolute nonsense. I mean, as a practical matter, once Team B hits population 0, the fighting stops. So yeah, I should also mention there's actually a really easy way to do this once you know the answer. So remember one of these differential equations that we started with, and I'll even keep the different k's. So given that it is an n squared law, well, what happens if we differentiate the square of that? Well, based on the chain rule, it's just going to be 2a times whatever that was, and I'm going to throw in a ka as well, just to make the result symmetrical. So yeah, d by dt of kaa squared equals minus 2 ka kbab, and d by dt of kbb squared, well, it's it's going to be exactly the same thing for exactly the same reason. So yeah, that's the square law in its more general form. So what we learned there is that effectiveness of an army depends on the square of its size, but it only scales linearly with its quality. So yeah, quantity has a quality of its own. I'm not sure who said that. It's often attributed to Stalin, but nobody really knows. So yeah, I suppose we shouldn't really go any further without checking, does Deuteros actually follow the predictions of this law? Okay, so that actually made a reasonably good prediction for most of those fights. So I think it's fair to say that Lanchester's law is in operation. Unfortunately, random numbers are also in operation, and that can screw us. I mean, one example I didn't show, the absolute worst one for randomness would be fighting 200 drones versus 200 drones. Lanchester's laws say that that fight should just dwindle down to 0 on both sides. But what actually happens is that due to RNG, one side gets a small advantage, which obviously snowballs. I mean, you've seen that 200 versus 190 can result in 60 drones surviving on one side, and the RNG can easily turn 200 versus 200 into 200 versus 190. So, in any maths lesson there is this dreaded question where just after the teacher has explained something, usually someone at the back of the class asks the question, are we ever going to use this? And this is quite hard to answer because the correct answer is, well, you probably won't, but maths teachers are not actually allowed to say that. But it's a fair question. It's particularly a fair question here because, okay, we can predict the outcomes of battles, but so what? This doesn't seem to generate any practical advice other than fight with the largest army that you can, which was obvious from the start. But actually there is something useful that we can learn here, and it's to do with the fact that in Deuteros you have, if a factory is attacked, you have 4 days to defend it. And that's plenty of time to do funky things like half defend it, then retreat, collect some reinforcements, and come back. And so, yeah, that's the scenario. Enemies attacking with a full-size army, you're defending with one, but you're allowed to run away and then come back. And the enemy army is completely happy with you doing that. That's a little bit implausible, but that's how Deuteros works. So the big question then is, when should you run away and come back? Like, how much damage do you have to take, or what's the best time to do it? So, completely, almost entirely irrelevant variable n is the starting size, and f is what we want to know. Like, what do my numbers have to get reduced to for when we should run away? So yeah, fairly simple model here. The first fight, obviously, more or less by definition, both sides are going to be beaten down to NF. Second time, when we come back, we've got N, they still have NF. So yeah, it's the square law again. Subtract the squares and square root it. So our defend is reduced to that unpleasant looking square root thing. So yeah, what we care about is casualties. Which means we just subtract what we get from n. Remember, we fought 2 battles, so we're fighting. So we suffered 2 lots of casualties. So that's the task: minimize n multiplied by 2 minus f minus 1 minus f squared. Well, square rooted. Of course, n is a constant, so it doesn't really matter. 2 is also a constant, doesn't really matter. And if we lose the minus sign, we're now trying to maximize that, which is related to what we've got left over. And there's probably a clever way to do that, but I don't see it. So we're just going to do it the stupid way, which is to differentiate it. So yeah, differentiating f is easy enough. Differentiate square root, you're going to get minus 2f, but you're also going to get a half from the root, so let's cancel. And then when is that 0? Well, that's going to be 0 when, since this is 1, when that fraction equals minus 1. Or when f equals 1 minus f squared, so yeah, square it, collect the f's, and f is the square root of a half, or 1 over the square root of 2. Which in practice means if you have 200 drones, then you should retreat once the number goes down to 141. And if you do that, you'll suffer 0.56A10 in casualties, which would equate to what? 120? No, 119. And that is a scenario that comes up in Deuteros plenty of times. But I'll think a bit further out of this. What happens if you have several chances to reinforce? A classic example would be if you actually have a ship stationed there and somewhere you can reinforce it just one day away, you can actually fight 3 times. So you can leave and come back and leave and come back over the space of 4 days. And if you've got 2 ships, you can do it 6 times. So this is my guess, but when you think about it, it kind of has to work. Fraction is square root of 1 minus 1 over b. So the idea there is that if you remember to square it, in every fight we're losing 1 over b of our strength. And then reinforcing and coming back, and also in every fight. The enemy's losing 1 over b of their strength. They're exactly b fights, so that will beat them down to 0. So yeah, we use this fraction each time. I don't quite have a proof of this. I'm pretty sure there is one, which I can't be bothered to write up, that it's essentially one of those proofs that say if you have any other method of doing it, then it can be made closer to this method, and also that would make it better. So some example, yeah, the classic example, b equals 3, then we should retreat when we get beaten down to 163. And if we do that, casualties are 0.55 of the total value, which would be 110. B equals 4, 200F equals 173. That's actually the first 3 digits of root 3. And casualties go down to 0.535, so then we'd be taking, well, I've multiplied that by 2, 107 casualties. B equals 6. Goes down to 0.523. It's not going down by much anymore, but a kind of a silly example, b equals 100, goes down to 0.501. So I think what was going on here is getting closer to a half. And that is the theoretical value, where if our casualties could somehow be constantly and automatically reinforced, then that is what would happen. We'd only lose half. So yeah, but these numbers are important. And this one I've done, or depending on exactly where I put this nerdy interlude, I will do a few times. Sometimes you do get to defend with 2 ships in one place, and have the ideal situation where you can where you have something 1 day away to reinforce. So yeah, that is the one useful thing that we can learn here, and that should explain my decisions when I choose to retreat and come back. Because the other thing is that RNG is a factor. Like, if the RNG hates me, I'll probably retreat much earlier, and if the RNG likes me, then I'll hang around for a bit longer, to enjoy the benefit of this RNG longer. But yeah, I hope that was interesting, and we can now go back to playing the game.